Actually, there are many photosol methods, at least some famous ones here. And what we want to use is a reflection of the laser, because thermal reflection method. Compared to the other famous methods here, our method have this good thing is give us a high spatial resolution, and it's easy to adjust, and from the cost factor is very cheap. Here is an idea of the thermal reflection method. The red laser here is a heating laser, and it will be injected to the surface of the sample. It's a composite sample, 2 layers. And the Prof laser, the blue one, will be injected to the same spot on the surface and reflected to this by this way. Actually, it's the same spot. It's easy to see here, so I use 2 lines. And the heating laser is a sine wave laser, so the heat source here on the surface is also a sine wave. And from the Prof laser, which is constant before the reflection, it will be a sine wave laser because of it can show us the thermal distribution on the surface. And what we want to get is a reflective Prof laser. And because of this thickness of the film, the sine wave laser will have a phase lag if we compare with the heating laser, which is also a sine wave. So the phase lag will give us information of the thermal property on this sample. Here's the
you set up
project
the system?
Now we're still setting up this system.
When we can see it working?
I think in 1 month maybe.
Last month?
2 months delay. We didn't want to know. So when you start to get data and show us, it's very interesting.
Okay, and okay, I think I don't need to spend much time on it, because I think all you here carry more calculus or math problems than our physical problems. Okay, here is a survey. We have 2 temperature function. You can see it's very similar with this one, just with the substitution. And here it means a film, and S means sample. The bonding condition, we have 3 bonding conditions. It's much easier to see if we write down like this. The bonding equation of the film and sample here. And the bonding condition on this interface is temperature is the same, and the heat flux is the same. And on the spot where the heating laser injected on, we have a heat source bonding condition. Like this. The same function here used to describe the sine heating laser heat source. Here is the. I think it's much easier than.
What is omega? Tell me what is omega.
Okay, omega here is this omega is frequency of the frequency.
Wow,
of the
I can see fractional calculus already. You got a square root of omega.
Okay. Here is one step in the procedure, in the solution procedure. I mean, actually we don't really care about the exact solution, but what we care about is real part and imaginary part of this solution.
Okay.
So if we pick out the real part and imaginary part, the phase angle here we can express the phase angle with this function, and so actually finally the result, it has a very simple expression, but here has a more complex expression.
I see this is a hardcore fractional calculus problem according to this square root omega here.
Yeah, but you also actually disguised something that you've done in
and that is the laser isn't a heat source. The laser is a source of electromagnetic radiation, and you need an impedance to transform it to a heat source. And how you determine that, and so you made an assumption about the impedance when the laser impinges on the material. That's a source for the fractal dimension about the properties of that matching. And so the transformation from radiation to heat, to temperature.
But that process, that time scale should be very fast. The omega here is not to that kind of level, electromagnetic wave. I mean, that's...
It's a forcing frequency.
No, but it's the time scale for the to make the transformation from electromagnetic wave to heat. That could be a longer time scale than the oscillation frequency for the electromagnetic wave.
Oh, yeah. But then this omega here is the modulation of the laser intensity. So it's a much slower process.
But isn't that related to this transformation from the radiation to the heat?
Radiation to heat is a much smaller time. And this modulation of the heating intensity is a much slower time.
Where does omega come from?
It's modulation of the laser intensity. So
So
you put it on the frequency.
Why is it modulated?
Well, so you can measure, so you're putting the sine omega t on the surface. And then you measure the surface temperature. And you can see there's a response, there's a phase shift of delta.
So it's a linear, you assume here?
No, it's just the solution of the heat transfer equation.
But you have the same omega, so...
Yeah.
Same omega means LTI assumption, linear time invariant.
I wouldn't know that. It's probably for our case is that our interest is to find out what this delta is. So it's not an absolute measurement of the response temperature. We only measure the response frequency shift of the response. And then based on the frequency shift of that long equation, then you can calculate what the properties are of these layers.
I think I had, sorry. Sorry. It's like this, this laser, the heating laser, it reaches the surface like this, and then the surface will have a temperature distribution like this.
Why?
But it's because of this heating laser is a sine wave laser. This omega is not the frequency of the
Yeah, I know.
light.
You keep saying it's the modulation. What's producing that modulation? That's what there's something I'm missing.
Sorry, I didn't see the.
Go back to the optical
So
layout.
that omega is decided by you.
Oh yeah. It's from a function generator.
Here,
Uh-huh.
this part.
But what is the best omega
okay.
then?
All right.
What?
What is the best omega?
Okay.
What if we change the omega?
Yeah, you can change the
There
omega.
are infinite choices of omega.
Right.
Which one you pick? Why pick this omega?
Because based on the sensitivity, uncertainty level, and all these parameters.
That part is even more interesting.
The frequency here should be 2 megahertz, and to choose this value is because of if it's too fast, it's not easy to catch up, and if it's too slow, the sensitivity of this experiment, will jump down. Yeah, degrees. Sorry.
That's interesting.
Because I jumped this stuff. So.
Okay.
This looks like a system identification problem in my field. So. And you use the very simple and linear time invariant assumption. Like you assume the back omega is the same, and only the phase shift and amplitude may be also.
No, it's not assumed. It's the solution of the long solution. So you can see, okay, from the solution, here is the simplified format. So you have this very long solution of one
If
page
you
long.
observe the different like input omega is this, while you pick up on the waveform, the omega is not exactly matched to this. Is there any observation on that?
You can go back to that long solution of the expression for the, that's the one. This is not on the surface. You don't have the one on the surface. Is this on the surface? Oh, this is on the surface, yeah. So the solution under the